All right, we're about to look at parametric arc length. With parametric arc length, we use the parametric version of ds, which is this thing right here. And when we use endpoints with parametric and with polar when we get to it, typically we use Greek letters for our endpoints, alpha and beta. But that's just a convention. It doesn't matter. If you want to use A and B there, go right ahead. But there is one subtlety we have to be careful about. If we want to find the length of the curve, we have to make sure that the curve is only traversed one time from alpha to beta. That's the reason this says distance traveled here instead of arc length. This first example we're going to look at is going around a circle. Well, if you only go around the circle one time, then that gives you the circumference of it. If you travel around the circle twice, if you calculate that, the distance that you traveled is actually going to be twice the circumference. So you have to be a little bit careful on these to make sure you don't double up your length. So let's take a look at this first example, which is what I just showed. Find the arc length and distance traveled by a particle with these parametric equations. X is sine t and y is cosine t. Now if you look at this, this is the unit circle, and so we know right off that this is going to be 2 pi, because that's the circumference of a circle with the radius 1, and that's going to be the distance traveled by this little dot as it goes around here and makes one lap around the circle, and it's also equal to the arc length. And let's do this though using the ds. So ds in this case, we have to find dx dt. Dx dt is going to be cosine t. Dy dt is going to be negative sine t. And so if we go and square both of these things, we get that our ds in this case is square root of cosine squared t plus sine squared t dt. And of course, cosine squared plus sine squared is 1. So our ds here is just 1 times dt. So our arc length, or maybe I should call it our distance, is just the integral from, let's see, we started from 0 and we went to 2 pi of dt. And so that just gives us t from 0 to 2 pi, which is 2 pi. And that's both our distance and our arc length, because we only traversed the circle one time. Now let's look at this next example. Notice it's very similar. We've got sine of 3t and cosine of 3t. Now if we were to graph this, going from 0 to 2 pi, it's going to trace out the same thing, the unit circle. But over the course of 0 to 2 pi, because of that 3 in there, it's going to make 3 laps. So if we wanted to find the distance traveled, it would be the integral of ds from 0 to 2 pi. But if we wanted the arc length, we'd integrate ds. We'd have to figure out when does it get back to the beginning, and that's going to happen at 2 pi over 3. How do I know 2 pi over 3? Because I know this is going to give us three laps around the circle. Let's play with Desmos for a second to see this. If I put in y, let's see, x, I don't have to put x equals. I'm just going to put in sine 3t, cosine 3t. And if I go from 0 to I put in 2 pi, you know, it just, all we see is the circle there. But notice, look at how far we have to go to get all the way around the circle. 2.1. That 2.1 is approximately 2 pi over 3. That to be b. If I make this end over here 2 pi over 3, you can see that 2 pi over 3 gets us to the end there. All right. Now, one thing you might notice, I made a mistake up here when I drew my graph. Really, my mistake was not on the graph, but on the starting point. I said that we were going to start over here at 0, but we didn't. Or I said we were going to start here, but actually this thing started up here and moved around in this direction. And same thing up here, because I had x was sine and y was cosine. All right. This is going to be a more interesting example. We'll put this one on the next video.